Alright, I know I'm a little late on this video, but I figure this might be a good review for people before their next test about concavity and curve sketching. It's section 4.4, and although I've talked about finding maxima, minima, extreme values, critical points, there are a few things about curve sketching that I didn't really talk about in other videos. And so what I'm going to do here is kind of do a brief overview of everything. So I picked a nice function to analyze, x cubed plus x squared. As you can see, it's got a nice amount of concave down, concave up. It's got a local max, a local min, so it's nice. So remember, to find the local minima, what we are looking for, local max or minima, otherwise known as critical points, is we are looking for when the tangent slope to a point on the graph is 0. Because if you're going like this, when your slope reaches 0, you're at a maximum, a minimum, or a saddle point. So your options are, you could be a maximum that has a slope of 0 at the maxima, you could have a minimum that has a slope of 0 at the minima, or you could have a saddle point which also has a slope of 0 but is not a maximum, neither is it a minimum, but it is a critical point. So those are the three options. And how we tell where those points are is we take the derivative of f of x. So f prime of x equals, using the power rule, 3x squared plus 2x. And so the idea here is if we set this equal to 0, so if we set the derivative equal to 0, we will be solving for all the points on the derivative graph that are equal to 0, which means that we're going to solve for all the points on f of x that have a slope of 0, thus making them critical points. And so here we could factor out an x from both of these, equals x, 3x plus 2, and this one's just really nice. So if x goes to 0, everything goes to 0. If 3x plus 2 goes to 0, everything goes to 0. So we know we're going to have two critical points. One is x equals 0, because if x goes to 0, everything goes to 0. And the other is when 3x plus 2 equals 0, if that equals 0, everything else will go to 0, so we'll solve for that. So 3x equals minus 2, divide 3, so our other x that's a critical point is minus 2/3. And so that's how we solve for critical points. And it looks like, so what I have drawn up here is just for referencing. You could actually draw this without knowing what it looked like by using these methods. But I just want to point out that it works. So x equals 0 is clearly this point right here. That's x equals 0. And x equals minus 2/3 is this point right here. And so we'll write that x equals minus 2/3, and this is x equals 0. And so we've found critical points. So the next step is, how do we know if they're maxima or minima if we don't have the graph drawn? And so for the next step, we're actually going to take the second derivative of f of x. So I'm going to take f prime of x. And looking at f prime of x, I'll take the derivative of that, bring down the 2, make it a 6x plus 2. Now this is now a linear graph, but I would like to point out that so when we think about the double prime of f, so when we're looking at f, we're looking at where something is. When we're looking at f prime of x, we're looking how it changes. And when we look at f prime of x, we're looking at how the change changes. So we've talked about f prime of x as slope. F prime of x is how the slope changes. So, for example, if I'm going from left to right, and the slope is decreasing, right? So the slope started out really steep here, and now it's decreasing. That is going to be the slope changing in a negative direction, right? Because the slope is decreasing. So that is indicative of a negative double derivative, because the slope, the rate of change, which is the slope, is changing at a rate which is causing it to decrease. Whereas over here, you'll notice the slope starts small, and it gets bigger, 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 bigger. So that represents a rate of change of the slope that is positive. And you'll notice that when the slope is changing negatively, where we end up is a maximum. And if the slope is changing negatively, or I'm sorry, if the slope is changing positively, we end up at a minimum. So negative slope rate of change is a maximum, positive slope rate of change is a minimum, which is kind of counterintuitive. So if you plug in a value, if you plug in an x value into f prime prime of x, it will spit out a number that's either positive or negative. If it spits out a negative number, that means that the rate of change of the slope is negative, and we call that concavity down. Okay, so the concavity is pointing downwards. That's concavity down. And if we plug in an x value, like say x equals 0, and we end up with a negative number, that's because, if we end up with a positive number, that's because the rate of change of the slope is increasing, and we correlate that with concavity up. And so let's go ahead and plug in our critical points. We'll start with f prime prime of 0. That's going to equal 2, right? Because we plug in 0 to 6x, we get 0, and that equals 2. So, based on the rule we just discussed, now x equals 0 on our original graph f of x is going to have concavity down because it's positive. Or I'm sorry, it's going to have concavity up because it's positive, right? So we look at 0 and it has concavity up, which means that the rate of change of the slope is positive, and that points us towards a minimum. So now we know that x equals 0, the critical point, is a local minimum. Okay, now we'll plug in f prime prime of negative 2/3 to find out what it is. So 6 times negative 2/3 plus 2, 6 and 3 gives us 2, that's going to give us negative 4. So this is negative 4 plus 2, that is negative 2. So what that tells us is that because this is negative, that means it's concave down at x equals negative 2/3, which means the rate of change of the slope is decreasing. And so what that tells us is that we're looking at a local maxima right there. So this one was a minimum, now we're looking at a maximum because we got a negative value out of the double prime of f of x. So x equals negative 2/3 is a local max. And you'll notice, I've got this drawn up here just for referential sake, but we could have not looked at this graph at all or not graphed it on our calculators and still figured out which were the local min and the local max just using this process of algebra and derivatives. Now I'd like to point out that if your second derivative does not equal a positive value, or concave up, does not equal a negative value, or concave down, but rather if it equals 0, 0 represents a saddle point. Because remember, a saddle point is where we flatten out and then we go back up again. So there is no concavity right here because it's split in between a concavity down section and a concavity up section. So when the double prime of that value equals 0, you're looking at what we call an inflection point. And so that's really important. Let's go ahead and find our inflection point for this graph right here. So the inflection point is the point at which the graph is no longer concavity down or concavity up. It's now 0. So if we set our double prime, f double prime equal to 0, so 0 equals 6x plus 2, then we will be solving for the inflection point. Because the double derivative represents concavity. If our concavity equals 0, we must be at a point between concavities. So right away we can kind of acknowledge it's probably going to be right about there. Because the concavity is down, 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 now it's concavity up. There must be a point there where it's 0. So we'll solve for that using the double derivative. Minus 2 equals 6x, divide by 6, divide by 6. And what you end up with is x equals minus 1/3. And this is an inflection point. And so that is about everything that I think needs to be covered. We've learned how to find critical points, prove whether they're maxima, minima, or saddle points, and then also find our inflection points. So I hope this was helpful. As you can see, our inflection point is pretty much right where we estimated it would be by looking at where the concavity changes. So I hope this was helpful, and I'll see you next video.